gonna talk about capacitance. The first thing about capacitance, we're gonna discuss a capacitor. What is a capacitor? So, we have that a capacitor is pretty much like a battery. So we have a battery, charge. What happens next? Both store electrical energy, but what happens inside is different. A battery, for example, is that produces a chemical reaction so that it produces electrons on one terminal and absorbs electrons on the other terminal. So that's how a battery works. But a capacitor is much simpler than that, because it can produce new electrons. It just stores them. So what happens? First of all, what is a capacitor? Capacitors are terminals, specifically two terminals of metal, separated by a non-conducting substance. We call this dielectric. So something in the middle is dielectric. This means it's not conducting energy, just the middle. You can easily make one capacitor. You just have two pieces of aluminum and a piece of paper, for example. So that is a capacitor. For the electric materials, we have different types. The first one is, for example, ceramic, porcelain, Teflon, plastic. We have others like glass. These different types of dielectric, it depends a lot of their use. Next fault, we have to tell you what happens when you make when you put, to understand better what is a capacitor, we're gonna make it a circuit. So we have a battery. This is a battery. Well, you get the idea. Good. Okay, we'll go. So this is a battery and this is a capacitor. The plate on the capacitor that attaches to the negative terminal of the battery, like that. This two accepts electron that the battery is production. So the plate on the capacitor that attaches to the positive part of the battery loses electron. So what happened here? Once the capacitor is completely charged, it will have the same voltage as the battery. So for a small capacitor, we have a small capacity. But the large capacitors can hold quite a bit of charge or a lot of energy. So you can find capacitors like these. Yeah, really tiny. And then you can have a capacitor of enormous like this. So yeah, it exists. They are difficult. A good example of a big and enormous capacitor, it will be a natural, and it is the clouds and the land. So we have these two. In the middle we don't have nothing, or air, for example, just flowing. So this capacitors, then when we have something that is called a charge releasing between these two plates, we get a lighting. So this is a big and enormous capacitor, but as you know, it is dangerous too. So we have a big enormous capacitor with a big enormous we have a number of capacity, but we don't have security. That is important to know. That is difficult. So what happens here is that I just want to tell you that the same voltage here, it will be stored by this one. It depends on here's size, but it is what it is. So what would be the next thing? Well, the next thing is how capacitors. What is a capacitor storage potential? So what is it storing? So a capacitor is storing, it calls capacitance. How much it can hold on, for example. So we have a capacitor, storage potential. What is this? Well, the capacitor storage potential is very simple. This calls capacitance. This is our main topic. So capacitance is measured in units called farads. SI. So we got farads. We got farads. Farads are the principal unit. 1 farad can store 1 coulomb. 1 coulomb. What coulomb? Obviously this is charge and it is at 1 volt. So we got that a coulomb is 6 point approximately 8 to the minus 28 minus 18. Sorry, that's my fault. And that what is happening here? It has a lot of electrons. So with this, we have to say that 1 amp, 1 ampere, is referring and represents a rate of 1 coulomb of electrons per second. So 1 farad capacitor can hold 1 amp of electrons at 1 volt. Okay, so 1 farad capacitor will be pretty big. You see the number already of 1 coulomb. So 1 farad will be approximately the size of 1 can of a soda. Pretty big, right? So depending on the voltage it can handle, it will be bigger or it will be smaller. So for this reason, capacitors are typically measured in micro farads. Micro. Sorry. My fault. Microfarads. Okay, so just to put you in context, we have that a battery has 2.8 amps at 1.5 volts. So if we want the same amount of in a capacitors, we will need 10,000 farads. So pretty big, right? It will take a size of a can, just 1 farad. So imagine what happens with this amount. You will have, I don't know, more looks like a spaceship. So it is impractical to use capacitors to store any significant amount of energy like that. So what are the main applications of capacitors? Because we have some applications, pretty important ones. So one important difference between a battery and a capacitor is that a capacitor can discharge pretty quickly. So you have that battery can discharge a typical battery discharge over a period of time. So it begins and it ends. Well, it ends at 10 hours. No, this is the dischargement of the battery. What happened with a capacitor? Well, a capacitor can discharge immediately. So that is pretty quickly. So that's why we have a lot of application. For example, what happened when we have a camera? With a camera, we have some previous photos. Exactly the flash. What happened with the flash? So the flash takes a lot of energy. So what it does, the camera has a battery and it charges the capacitors. When we need to use it, then it discharges automatically. Something we can do with the battery. Another examples are like TVs. So this is very important because we have problems, and that's why they warn you about opening a TV or opening a flash unit, because these big capacitors can potentially kill you if you have received a lot of charge. So what other use? Capacitors are already used in lasers. Other are like, for example, in spaceships. Other examples include microphones, and we have a lot of examples. Well, we talk about capacitors, and I want to talk about capacitance. What is capacitance? Well, we hope that capacitance, see it? Sorry. Is the potential storage. So unit will be, of course, column over volt. This is equal to farad. Why? So this is not a C, sorry, this is Q. Q is the magnitude of charge. Is the magnitude of charge stored on each plate, okay? And then the volt is the voltage applied to the plates. Apply it to the plates. And you have to better understand it. So it is like, for example, pretty the same as an air tank. So we have a bump, then we have a bottle. And it has air. So what is the capacity? The capacity of this bottle is the volume of air stored sorry. Volume of air stored. So it is the magnitude of air that is in the bottle. And then from the total capacity we have to the pressure applied into the tank. So we have that the capacity of these tanks is obviously the same as the magnitude over the voltage, because voltage is applied to the plates as the pressure is applied to the bottle, and the magnitude of charge applied, it is like the charge stored and the air stored. So it's really simple diagram just to understand what is happening here. Okay, next we're gonna make we're gonna explain. So we just have capacitance. We just see the circuits, and then we have to tell you that there is capacitors in series and capacitors on parallel. So for these two, we're gonna make some really good examples. First of all, capacitors on parallel. So I already tell you what happens when you have a circuit and you have like this type. You have a capacitance right here. You have a voltage right here. But what happens when you have more of this and you put them in parallel? Like that. It's more interesting. So what is the same thing in each one of these? Because you don't have the same current or the capacitance, because you got electrons flowing, but they are dividing over these three, so you don't have the same capacitance. So what you can have the same voltage, right? Because these are in parallel, so you have the same type of voltage in each one of these ones. So just to make it more simple, you have B1, then you have B2, and then you have B3. But these ones are exactly the same as the battery, as I told you, because the battery is B0. But the other ones are charging by the battery, so they have the same amount of voltage. What is different right here is the charge. And the charge total charge, it will be like the sum of each one of each of them. So if we know capacitance is equal to charge over voltage, then if we want to know what is happening with the capacitance, No, you know what? What is happening with the charge? So charge is equal to C times B. So I got Q total equals C, the capacitance, times the voltage. That is the same. So what happens here is that we got that C is something equivalent. And this equivalency is about the next diagram. Why? Well, because if we can make the circuit much simpler like this, because it has the same voltage and we have different charge, so the C equivalent will be to the sum from the beginning the first one to the last one. So this is how we get the equivalent in these capacitors, call it capacitance, sorry. So this is a very good example. But what happens when we have capacitors in series? So the next drawing will be not that. It will be like this. So it is getting the same it is getting an initial voltage. Thank you for the battery. Obviously it has some polarity, but what happened next? The next thing is the most important, because what is the same for each of these capacitors? Well, the voltage isn't. Why? Because the voltage is distributing about each one of these. So you don't have the same voltage, right? And then you have some chargers. These chargers, because they will eliminate, they will become neutral on this part, because it has the same amount on this plate and on this plate, and this is negative and this is positive, so it says that this will be neutral. So it is like we have a neutral over each this one over this one, so we get a bigger one. Capacitor. That is our capacitor. What happened next is that obviously the voltage, it will be not the same. We have a total voltage, and then we have a battery voltage, and then we have B1 plus B2 plus B3, like that, because we are adding each of the voltages. But as I'll tell you later, we got our charge is equal to our capacitance times the voltage. So if we want to know what is the charge, so we have to tell C1, C2, and C3, but they are not the same. You know what? We have this we can make this. So we have the voltage, the sum of the voltage. But we want to know this difference. So for this difference, we're gonna add each one of these. There is Q. Q is the same one, as we see. But what is different? The different thing are the capacitance. The capacitance is summed like this. Oh, it's no Q, C. So we got the sum capacitance very simple. So that is our that is what we get with the voltage, and this is why this Q over C1 it is the voltage of number 1, Q over C2 is the voltage of 2. So we got the same thing. So we got that B total is equal, if we get Q equivalent, then we have to tell we have to C equivalent, and the C equivalent is gonna be 1 over C equivalent. It will be the sum from 1 to n of 1 of Ci. So that is what happens when we have capacitors on series, and this is the same because if we simplify the diagram, we have one capacitors, but we have different shapes, and we have different types of energy storage in different manners. So we have one of series and one in parallel. This is because and it is interesting because if you compare it to the letter of Ohm, this one is linear. It's a linear relationship. But when you get this one, the voltage isn't really linear. So we have that Q is inversional because of this. So this will be inversional. So that's why the normal circuits of series and parallel will be exactly contrary. So, and this is because this similarity between those. Just let me erase these ones. Okay, well, our next part of the video will be about solving problem number 6 of our unit of capacitance. Okay, so we will continue with problem 6. First of all, we have our diagram. The first step here is that we have a battery, minus, plus, our voltage. Then we have one capacitor, and then we have an array of capacitors. These capacitors are in parallel, and this is an equivalent of a series capacitors. But first, we mm, consider all the data that it is given by the problem. Okay, so we have that the voltage right here is 14.9 volts. Then we got 3.2 nanofarads. No, 3.7, sorry. Then we got 1.3 nanofarads, and finally we got 3.1 nanofarads. What happened next? When we have all these problems, and the question is, what is the particular no, sorry, where it's the potential? Yeah, just a fancy way of saying that, but potential, the potential across capacitor C2. We have our capacitors that it is C2. Then we got the capacitor C1. They are asking us about the capacitors. Yeah, C2. What happened next? So we get the voltage across that capacitance. But the most important is how we are gonna get the voltage of this capacitor. Just to don't make any confusion, I will rewrite it. So C1, C2, and C3. Okay? First, this is our problem. We have to solve it in two by looking at these similarities. First, we have this part of the problem, and then we got this part of the problem. So expand that, and we have two parts of the problem, two main parts of the problem. What happened next? Well, we have a series of capacitor on series. Yeah, we have a capacitor on series. You know what? We're gonna make first capacitors in parallel. Yeah, just to better understand everything on little pieces. So we got that our capacitors in parallel is just something is this part. So what happened when we have these capacitors or parallel? Well, first of all, we know that when we have capacitors in parallel, the voltage between these ones is the same. The things that is not the same is the capacitance, because the charge is distributing by different sides. So of course we are not having the same charge on this, but we have different charges, but we preserve the voltage. Okay, and the capacitance it's not the same because the charge is not the same. But we got that B1 like that. So we got that B is equal to B1 like that. Okay, why is this one? Okay, if you want more appropriate number, we're gonna make this 2. The voltage it will be the same. Okay, the thing is that it's not the same. Our charge that it gonna be a sum. It will be a sum of these two. You remember in parallel with sum, like normal, by adding x1 over the other one, and then what happened is that we need some other evaluations to really do this. Okay, so we have C1 and C2. Oh, there's no C1 and C2. Actually, it's C2 and C3, but it's him. So I will put just our equivalency C2, C3. That is our capacitance. What happened here? Our capacitance is just really the sum of C2 and C2. Pretty simple. We substitute our previous data, and then we got 5 nanofarads. Okay, so that is some thing. So remember C2 and C3 now. It's a capacitor like this. Okay. And then we got the series. So we have the series capacitance. What happened with the series? So we know that this voltage will not be the same. Okay, we got different voltage. So we got B1 and B2. Remember that the voltage is the thing that it changes. Okay. So what happened next? Well, what happened next is that we have to make the sum of these capacitance, and we have to make an equivalency of these two. Of course, when we have to make this equivalency, we don't just sum, because these are in series. So our proper way to do it is to make a C equivalent 1 over C2 and 3 plus 1 over C1. Okay, so we got that equivalency. So we solve that part of the problem, and then we get something like this 3.1. Well, just to make it coincident. Like that, okay? Then we have to solve like this division. And by solving it, we will first make it like normal. I just want to make something, but it's okay. So we got that. What happened with this? Okay, so what we do is we make this happen, so we make this happen, and then we can have an equivalency, a capacitance equivalency that it is simple to read, more natural. So we got this approximately 1 point minus 8, 1.9, sorry, by 10 nanofarads, Faradays. Oh, Faradays. Okay, so what happened next? We have our equivalency of these two capacitors. Okay, and then we have to make some thing called C equals to the charge over the voltage, so that we can find the voltage specify this B2. Okay, so right now we are gonna say that first this, just remember this data, remember it. And for the parallel, we will extract Q, that is our sum of charges. As we see on parallel, our voltage is the same, but our charge is not the same. It is the sum of it. Okay, so by making the sum of it, It's very simple because now we have that our voltage Q. So we got Q is equal to CB. So making this, we got that Q is equal to the capacitance. Capacity, remember that the capacitance over these two in parallel, we are making the parallel one. Don't forget that we are making this. This is 2, this is 3. So C2 and C3, they sum each other like normal. Okay, so they normal because they are some because they are in parallel. So we get something like this: C2 by B. In this case, is doesn't matter. Then C3 and B because it is the same voltage. Then what happened here is that we have to factorize this, and then we got B C2 plus C3. So we got Q. So we have Q, and then we have B, C, B times C2 plus C3. It's equals to the C equivalent that we previously calculated by the voltage total. Okay, so these B are doesn't matter because these ones are the same. So we are trying to calculate B2, but it is the same as B3, so we can have this by like B2 and doesn't make any change. Okay, then we just make this to look more beautiful, and then we can have our final result. Okay, so that is our final operation, and for that final operation we can have our final result. Our final result, it will be that B2 equals 5.70 24 volts. Okay, so what is important to remember on this type of problems? Well, first of all, then when we have on parallel, you just sum the charges, the capacitances like this. When you have on series, it's important that you sum capacitance like this. Okay, so that is our problem number 6 of our unit. I hope you like it. Okay, just our final topic is what happened with the capacitor with dielectric. We already talked this a little bit, but we have to say what is happening here. What happened in dielectric is that there is between the space of two conductors, it is occupied by something material that is not conductive. I already put this example, but just to make it clarified. Okay, what happened with that? So the capacitance of these capacitors, it raises and makes it by a factor K. Okay, so this K is called the constant dielectric constant of the material. This is of the material. And the quantity, it calls epsilon equals K times epsilon 0. So this thing is called permittivity of the dielectric. So for a fixed charge on the plates of the capacitor, the charger on the flat superficie sorry. They are called, it called okay, so we have that this code called permittivity. Okay, so what happens next is when we have a capacitor between two parallel plates with a dielectric, we have this example. Okay, then we got the capacitance 0, and then we got a K, but epsilon 0. But what happened here is by the area between the distance. Okay, it's really not that difficult. So what happened next? Well, if you want how to solve this, one example is the law of Gauss. That is that this law have the same shape as some space with two different things. First is the total energy that it is substituted by the same constant. And then we got that, and then we got that Q enclosed. Do you remember that? You close something, but when enclosed free. But that is that it just included the free chargers, not just the all the charger there is making a relationship by the all the Gaussian superfice. Okay, so we got like this really simple example of how to do this. I would just put the formula so that you know it better. What happened with dielectric? Well, we have our integral factor, and then we get our new, call it like that, field by dA, like that. Our previously area, this is a vector, sorry, and then this is equal to Q free, closer to free, divided by epsilon 0. So it's pretty similar, but we have to see these little changes on our formula. So that was our unit number 5, that is capacitors, capacitance. Okay, so remember this unit 5. If you have any further questions, please ask me, and I am here. And I don't know. That's all for today. Thank you guys. Yeah, super important. Don't forget these formulas, please. Get it on your mind. And this one too is important to know that this is equal to epsilon A over distance. Okay, so all of the problems are solved with these ones. We have a specific one and something that changed, but with cylindric and spherical, but you have to use the same formula. Okay, guys, thank you. See you next